this could be tedious, but this first step is one of the simplest. So we now come to the 2D truss element. 1D, no issue, okay, because just a Hooke's law and some more writing one equation or two equations is no big deal, okay. But if you start to handle 2D problems, okay, it's going to be more useful and realistic. Okay, this is a 2D problem that we're going to solve. Okay. So in this case, if you are going to solve, let me try this by hand. Okay. If you're going to solve these two bits, I mean, it's quite a straightforward one. Okay. Okay. So we learned about this element subjected to force 1, force 2. Okay. So if you do force summations, okay, on the left hand side, okay, U1, U2, okay. So if you I left node, okay, when you're writing equation, you're writing force sum on the node is equal to 0. So external force is F1. Okay, forward, no issue. And then next, the internal elastic force is when you do the compressions. So there will be, if you move it to the right, then you're going to get a force back. So what is the force back? This force back is K, and then U1 minus U2. Okay. Likewise, you're able to write these, okay, F2 minus what? F2 is forward, yes, that's fine. This is force sum in two directions. Like this. So for this problem, we have this force sum on node 1 and node 2. So I now copy it here. Force sum on node 1 is equal to F1 being the external minus the spring force, and then Ku minus K equal to 0. And then how about the force sum on the node 2? Let me write them in the different color. Okay, then you have the force sum on the node 2. Then you have this external force F2 minus the spring force again. But this time around, because you are moving it rightward, then you're going to have a backward Gaussian force. So you have a K, and then U2 minus U1 is 0. We now write them in the matrix form. Okay, one thing we take note of is because the force is both rightward positive. So let me rearrange the equation in such a way that I have the K U1 minus U2 is equal to F1. Likewise for the force sum on the second equation, then you're going to have the force rightward F2 then the left hand side you have the minus k u1 minus u2. Okay, one thing that we can do is we try to rewrite these as a matrix. So in this case, the right hand side is what you call the force vector. Okay, and then the left hand side is pretty clear. This is going to be the Hooke's law, but this Hooke's law is going to have the matrix times the displacement vector. And what this matrix? Okay, the first equation you write in the first row of the matrix. Then you have k u1 minus k u2. Then next, you have the second row of equation. Then you have the minus k u1 plus k u2. Okay. So when you try to handle the question here, okay, two pairs spring supporting one mass or one bag. Okay, so you can see this mass as mg. Okay, but if you now focus on two springs, okay, you see that the external force is going to be mg divided by 2 on both nodes. And then you have the reaction force, let's say R1 here, let's say R2 here. No, this is not 2, this is R3. Okay, and then what are the equations? What are the elements you have? The element you have is basically not 1 and not 2. But according to our convention just now, according to our convention just now, okay, so any force, okay, must take the same direction convention. Okay, this, if it is downward positive, the force are all downward positive. Okay? So if you now going to write the equation, what are you going to write here? Okay. Let's see the first element. Okay? For the first element, you have element number 1, which connects not 1 to not 2. Okay? Remember this equation, then you're going to write, if this is K1, then you have the K1 minus K1 times K1 times U1, U2 is equal to what we call the force F1, F2. Okay? But here, the F1 is equal to minus reaction force R1. This F2 is equal to mg over 2. Okay? So then you're going to do the update. Okay? You're going to have the minus R1. Okay? And then likewise, how about equation for element 2? For element 2, you basically have knot 3 connected to knot 4. Okay, then you're going to write the stiffness matrix and displacement vector. In this case, this is 3 to 4. Okay, and then the reaction force is minus R3, and then here you got mg over 2. Okay. So in this case, you're now going to have two equations. But the next step is, these two equations, what the name are? They are the force side. So Newton's first law. Okay? So that's why we every time say Hooke versus combination of them. Okay? So, but usually we don't do the force sum arbitrarily. If you want to do force sum arbitrarily, you're going to overload yourself. Okay? What would I say you're going to overload yourself? Okay? Please forget about the element assembly in your textbook or whichever textbook. What you did for element assembly is nothing more than writing these force sum on each node. Okay? You might write equation for individual elements, but your system, this is the system force, also called the global force, is going to have everything together. So in this case, you're going to have U1, U2, U3, and then U4. Then you just take these expressions, okay, into your system matrix. Okay. So why would take time to do this? Because this is going to be the burden for most of you who don't do matrix method. Okay. Many of you, since you know bookstore, okay, you will not resolve the matrix. Okay, but we just give you an idea how bookstore is related. Of course, you are not going to solve this. So why you are not going to solve this by matrix? Because this is the singular system stiffness matrix. Okay? What means singular? So it's a symmetry one. So you take this. On the diagonal side, you see there are diagonal symmetry. Okay. So anything on the opposite diagonal, they're going to be equal. And then next, how you really solve it? If you don't bottom out matrix, you're going to start applying the boundary conditions. What's the boundary condition? Okay, you have the U1 equals 0 and U3 equals 0. So what are the free nodes? Your free nodes are U2, the node, and U4, and U node. Okay? But now, if you say, why not I simplify my question? If this is balanced, okay, am I going to write something? Yes, you're going to write something. You're going to write U2 is equal to U4. Okay? So this is the ideal case that you do the simplification, go equal to U. Okay? Yeah.
Yep. That one is U4, right?
Yeah, U4. Yeah. So this is assuming that they are moving in parallel down. Okay, that's fine. Okay. But what happens if it's not moving in parallel? Okay, you need to write the third equation. I'm coming back later. So let's assume this is true. Okay, then what you can do? You identify your free nodes. This is a free. This is a free. Okay, and it happens to be equal to U equal to 0. Okay, so if you now add the two equations together, then you have your K1 U2 plus K2 U4 is equal to the sum of the forces. Okay, but to be honest, you got to write clearly. This is what you call matrix operation. Okay? It has no physical meaning. It just helps you to do the solution. Okay? Okay? The physical meaning is you take this whole bar as one whole rigid body taking up the loop. So from here you have the K1 plus K2 U is equal to mg. So this is the solution. Okay, so please try to learn these operations. So don't just use your Hooke's law. I know everyone knows Hooke's law. You write separately. Okay. Then next we come to the case that you can't apply your Hooke's law immediately. Okay. You still be able. Next question we're going to solve. We have the cluster questions of 1 mass and 3 spring. Let's say the spring is going to be K1, K2, K2, K1. Okay? How much is the displacement when the weight is acting on that? Okay? So this becomes difficult. Okay? The motion is coupled. Okay, if you think this is this cross spring, if you now do the rotation, it is possible to write K1 supporting the mass, okay, mass M, and then this is your K2. Yeah, in this case, then you are able to solve it quite clearly. Okay. But we don't have the same questions because this 90-degree, this 45-degree turn, this 45-degree turn is giving you different static deformation. And so far, if you are using linear mechanics, so you know the vertical displacement V. Okay, you know this is going to be K1, 2K1V is equal to 2mg. And then horizontal displacement, 2K2U is going to give you 0 force. Okay, so this is the force sum in the y direction, and here this is the force sum in the x direction. Okay. So now, how do you handle the first case? Let's look at the analysis by mechanics first, or by free body force diagram, since you are more familiar with that, before we come back to the metric method. Okay. So let's consider this case. So good thing here is this is going to be a diagonal symmetric system. Okay? This is the K1, this is the K2, okay? And it's going to be K2 here, K1 here. If you now want to move the mass horizontally, this is what you call global displacement. And here, this is vertical. We have the global displacement. U in the horizontal direction. And then next, you have the V in the vertical direction. Okay? But to a spring, I don't see vertical and horizontal. Let me take this example of the spring on this side. Okay? If you now take an exposed view, the northwest corner is fixed. this southeast corner is moving horizontally, it's moving vertically. Okay? But to a spring with in that orientation, okay, you care about their axial force. So what's going to be their axial force? Their axial force is along this direction. Okay? So in this case, and how much the axial displacement, you only care about if you're going to have an axial force, okay, then you're going to have axial displacement. So what's this axial force? The axial force is going to be Fx, Fy. Okay? So because to spring, so what you have to do is you got to write this into the orientation. Okay, this could be a bit the orientation a bit tricky. So let me take another element. I want to take another element, which is this element. Okay, this element is the one in the first quadrant. Okay. This is very good. Why? Because, okay, it's going to, okay, I'm not going to take that one, I'm going to take this one, okay, instead. The element in the first quadrant, this was supposed to be the fourth quadrant, but since this point is fixed, and then this point is moving, so you have a U and B. Okay? The angle here, okay, is let's say theta. Okay? Then you can see the force here, Fx, Fy. These are all the global coordinates. But to the element here, I want to see it along the element axis. How much is the extension force along the spring? How much is the displacement along the spring? This is what we call a local coordinate. Okay. To do this is not too difficult because you know, since force can be projected, this is Fy, this is Fx. If you draw this direction, how much is the total force along this direction? Okay, so your force here is the force up along the direction. Your axial force, we give it a name, axial force, is going to be what you have, force up in the theta direction. So this is theta. So if you do the projection of Fx, then this is going to be the sum of Fx cosine theta. Okay? And you do the sum of you do the projection of Fy. If this is theta, this is what? 90 degree minus theta. This is right angle, then opposite must be theta. So this one you have the sum of Fy sine theta. case, let's see, we have the force sum along the axial direction. Next, how about the displacement? Okay, let's draw again. Your displacement is u and v. Okay. So in this case, yeah, how would be the displacement look like? Okay, let's see. So this one you have the u. Okay. Let me write this in the big U to distinguish from small u. Okay. So in this case, this is still theta. Your u is the sum of displacement in the theta direction. So you can write down big U theta plus big V theta. Okay? And the projection here, how do you write them? Okay? You can write them the same way. This is big U cosine theta, and then you have the big V sine theta. Okay? And recall your equation here. You have the K is K2. Okay, now I have to write K here. Okay. The element we had was in terms of local displacement. Okay? Here you can do the expansion of the force. How do you write the expansion of the force? You write the expansion of the force as, let's say, F1x cosine theta plus F1x, this is F1y sine theta. Okay? Likewise, if you are writing for the second equation, you're going to have F2x cosine theta plus F2y sine theta. Okay? From the force side, you can write them like this. But another way of writing this force is what? Another way of writing this force is I can write a force vector F1x, F1y, F2x, F2y. Okay? How many elements? How many rows you have? You have 2. Okay? How many forces you have? Not one force in the x direction, force one on the not one in the y direction, force two in the not in the x and y direction. So you now have 4 times 1 forces. But in the end, you can enter them into 2 by 1. Okay? So the matrix to turn these normal forces into the axial forces. So this is the global, and this is the local. Local means axial. Okay. So you have to pre-multiply them by a matrix. What is matrix? This matrix is what you call a 2 by 4 matrix. They got 2 rows. The first one is going to be your cosine theta. Second one is sine theta. Okay, and then it doesn't multiply forces on the second node. Okay, and then in the second row, you only multiply forces on the second node. So it is again cosine theta, sine theta. Okay. This is what you call your rotational matrix. Okay. So here you got a rotation matrix. Yeah. Apparently, you can do the same thing, okay? But, yeah, this might not be what you want for re-expression here. Yeah. So, another thing that we can write here is, yeah, you can write them into from 2x1 force matrix. Okay, you already can write them into 2x4 matrix times 4x1 matrix. Okay, so this is the whole thing you can write. Okay, so means you're almost getting the force sum in the x and y direction, but on the left hand side I still have the 2x2 matrix and 2x1. So this is something trouble. I can do the same, but yeah, it's a little bit troublesome. So let's see how can you re-express u1, u2 directly to capital V and capital U. Okay. So let's do the re-expression. Last week we discussed it before. Okay, you can see here. Right. Yeah, we basically have the displacement projected, global displacement projected into the local view. Okay, so it's almost the same as we did. But for the force, yeah, we don't want it to be expressed as we did because, yeah, I mean, it gives you the same expressions, but it didn't help you to get the global stiffness matrix. Okay, let me re-express this again. This projection is a bit different from just now. Okay, let me write the equation there. What's the intended operation I need? The intended operation I have is I could have a spring which is required. But how do I relate them to a spring which is horizontal? It has displacement u, it has displacement u, but this is with the angle direction. We used to write this in a very simple form. This is the knot 1. This is knot 2. You have horizontal U1, U2. You have the force 1, force 2. And this is K minus K. My plan here is simple. My plan here is could I rewrite the thing? So what we did just now is I can write F1, F2 to be CS 0000 CS F1X, F1Y, F2X, Y. Likewise, I can write my displacement U1, U2 to be CS 0000 CS U1, V1, U2, V2. So if I do the re-expression here, okay, I'm going to have my K minus K, K minus K, then you're going to have your CS 0000 CS. You got the U1, V1, U2, V2. All these are the global one. Equal to my what I call C0000 CS F1X, F1Y, F2X, F2Y. Okay? Now, if you're going to write this is what you call a rotational matrix. A rotational matrix. Okay? But to us, this one is in front of the fourth vector is something we don't know. Why? In the case of solution, I want to write one simple clear equation. What's the target? The target is I should have one stiffness matrix which is written in terms of global displacement. Big U1, big V1, big U2, big V2 is equal to F1X, F1Y, F2X, F2Y. This is all global. Okay? Why do we want to write this? Yeah, this bear more physical meanings. If you read the equations, according to Hooke's law, stiffness matrix times displacement vector is equal to the force vector. Okay? So this is not the one we want. Okay? You have made the first attempt writing them in terms of the global forces, but the rotation matrix here is simply making the thing bear no physical meaning. Okay? So next, what should we do? If you can't express local, if you can't express, just now you attempt to use you express the local force in terms of global force. why not we change the role? Because our target is to express global force. So that will be very simple. Imagine the same spring element. If your interest is only global force. Okay? So in this case, okay, you can project the local force F1 into the vertical and horizontal component. So you have F1x, F2x, F1y is, what do you have? You have your F1 cosine theta and F2 sine theta. Okay, if you do the same on the other two notes, you have the F2x, F2y. Then you can write now the global forces into F1 cosine theta, F1 sine theta, F2 cosine theta, and F2 sine theta. Okay? So another way of writing this is what? Another way of writing this is, okay. So now our purpose of writing is different. Our purpose now is to express in the global forces. Again, I will reiterate. This is the normal force method. Okay? So you basically have F1x, F1y, F2x, F2y. What can be written? It can be written into, this is what? 4 by 1, and this is 4 by 1. How many variables you have? 2 variables. I can now write this 4 by 1 matrix into 2 by 4 and 4 by 2. You can write it to be 4 by 2 times F1, F2. This is 2 by 1. Okay? So this transformation you must take note of as we tell you what is finite element. Structural analysis by matrix. Okay? So you must be able to re-express this force vector into a matrix, okay, of the right size, then do the transformations times the unknown variable. Your unknown variable got 2 force. Okay? Then there's going to be 2 by 1. So look at the equation here. The first row is coming from this F1 cosine. Let me write C for cosine. I only have cosine times F1, that's it. And second row, sine times F1. It got no multiplication with F2. Yes. And then the third row is 0 times F1 and cosine times F2. And then the third row is going to be 0s. Okay. Okay, with this is the force vector. You can say normal force. Okay, and then next, northern force in the x and y directions can now be expressed as, what's the name here? Don't say it is element force. Nobody knows what's the element force if you go back to undergraduate university study. This is simply axial force. Okay? Axial force on node 1 and node 2. Okay, with this, then what do we go next? Okay, we're going to do re-expression. Okay, also re-expression. You can recall what's the matrix, force matrix here. F1, F2 is equal to K minus K plus K times U1, U2. Okay? If that's the case, then you can do further expansion. I have my C0 S 0 0 C0 S times what? Times K minus K minus K K times U1 U2. Okay? And can you recall what did we write for U1 U2? You can rewrite this in terms of the global displacement, big U1, big V1, big U2, big V2. In terms of the projection, do you remember? Just now we write this is CS0000 CS. Okay? So this expression can be further written to be so this can now be written as what? I write it over here. Your force vector F1x, F1y, F2x, y can be written as CS000 C0S times K minus K minus K plus K, and U can be expressed as what? 4 by 2, 2 by 4 and 4 by 1. So this can be written as CS000CS, and this can be written as U1 U1 U2 U2. So I repeat, this is the 4 by 1 vector of force. This is a rotational matrix, being 4 by 2. And this is my 1D stiffness matrix, 2 by 2. And this is another rotational matrix, 2 by 4. If you are not sure, we are talking about row times column. How many number of row and how many number of column. In this case, you are having a row vector. This is a 4 by 1, 4 row, 1 column. So this is a column vector. Okay? So with this, okay, we're going to do some operation because we know this is my global stiffness matrix. Okay, if I define this is my rotational matrix, you can see this. This is the transpose of my rotational matrix and my small element stiffness. Okay, and then this one is the global displacement vector. It's equal to my global force vector. OK， 所以同学看到吗？我们整个这个推算过程是什么？在每一个节点上的力和 OK， 力用什么表示？你可以是弹簧的走向力，但是我们选择了用坐标的水平力跟垂直力，所以一个节点就有两个水平，就是一个水平一个垂直力，然后两个节点就4个 ，OK， 然后现在你要把那4个力用4个位去写成福克定律，这个时候你就要用转动矩阵 ，OK。So in this case, you are writing the force, nodal force in the x and y direction in terms of the displacement in the x and y direction. But clearly, previously you only learned a spring deformation along the x direction. They are all local. But you now try to write them in the xy plane, so you have to do this rotation. So basically, the matrix you got, stiffness matrix you got to be pre-multiplied by a rotational matrix transpose and multiplied with the rotational matrix. And in this case, you obtain the global stiffness matrix. Okay? So we define the name first, and then next we do the operation. This operation can be tedious. We do one by one. Let's first do the first half. How do you write? You have the first two multiplication, 4 by 2 times 2 by 2. So before I finish this operation, do you know what's the outcome? It is still 4 by 2. So then you have the first row, first column, and then first row, second column, and then next, what do you have? You have the second row, first column, and then second row, second column, and then next what do you have? You have your third row, first column. What's that? That's going to be your KC. And third row, second column, going to have your KC again. And then next, come to the last row. That's going to be your minus KS. This is your KS. Let me see if I got it right. This is first. This is going to be minus. This is going to be the positive. Okay. You have the multiplication of the two matrices, and then you do the last. So what this to be? Okay, we need some space. Let's write this here. Okay, and also for your information, so in this course, we actually will let you handle simple problem that you can solve by hand in the final or midterm examination. So this is then going to test your derivation. Okay, so you better go back, try it out yourself, because when the questions don't have number but just simple, it really tests your understanding of the concept. Okay, we won't test your mathematics. I know you are not MATLAB, you are not any computer, so we just test your brain. Okay, so they were remarked by your senior. They are saying, "Sir, why you keep changing boundary condition?" Okay, so in reality, finite element depend very much on the boundary condition. What can I test you when there is only 2 degrees of freedom or 3 degrees of freedom? Okay, I wouldn't test you the analysis of Eiffel Tower. Okay, I only test you a bracket. Okay, but we could have variation of the boundary condition that tests your concept. So you better go back home, rewrite it yourself, try to understand it from the mechanics point of view. I intend not to teach this as the numerical solution classes. That was the method developed in 40s and 50s. Okay? At the time when computers is something a scarcity. Okay? Today, okay, any computer is already a supercomputer. Okay, last time I do the calculations of topology optimization 30 years back. Okay, I'm running MATLAB for 1 week for one result. Okay, after optimization. So today there is no point I test your computing power. I only test your brain power. Okay, but try to learn some symbolic analysis. Let me complete this multiplication first. Do it by yourself, by hand, then you are smarter than a computer. Okay? First row. What would I have after this multiplication? Okay? Before you do any matrix operations, please look at the size. This is going to be 4 by 2 times 2 by 4. So in the end, you're going to have the 4 by 4 matrix. Okay? What is the first row? Okay, anyway, we draw the row first. Okay? And we draw a column. Okay? My first row, first column should be multiplication of the first row and first column. And then you have your AC square. This is your first row, second column. Then you have the minus KCS. And then the rest 0, 0. Is it? No, not really. I think not 0. Okay. I jump too quickly. First row. Okay. And then first column, first row, second column, and then first row, and then the third column, you have the minus KC square, and then you have the minus KCS. Okay, if you repeat the same operation, now we look at the second column. We now look at the second row. Then you have this. What do you have? You have your KCS. You have your KS square. You have your minus KCS and minus KS square. Then now next move to your third row. The third row is minus KC square, minus KS, and then you're going to have your KC square, and then you're going to have your KCS, and then finally come to the last row. Then you have your minus KCS, and then what else? You're going to have your minus KS square, and then next you're going to have your KCS, and then you're going to have your KS square. Okay, please try to do it yourself, then you know the operation. Now let's factor out the common term. You can factor out the common factor K, and this is now your C, your sort of like a complete stiffness matrix. for 2 by 2, then let me see. This is positive. Okay, you can have a quick check if you are writing this in the right form. KCS, minus KCS, yes. And then this one is C squared, CS, and then the last one is minus CS, minus S squared, and CS, S squared. Okay, a quick way of checking, are you writing the right thing? There is one feature that we can always make use of. For any stable structure, stable, right? Okay, their stiffness matrix must be diagonal symmetry. Okay, meaning anything on the opposite side, you must find the identical. So already can find them there. And then how about this one? Yeah. You can also find this here, identical. You can also find this one. And then next you can also find this one. Okay. After this quick check, okay, you should be no problem getting the right equation. Okay, this, then we have derived the equation. So really, after you master that, you only need to do matrix operation. Okay? Okay, the reason I spend time on that is, to the first timer, you really have to put in some effort to try to solve it. Derivation is not what we every time do. We do it one time, but we're going to use it many times. Okay. So the first thing we define here is for all the elements we define, it is the element in the first quadrant. The elements start from origin pointed to the distal end. So in this convention, node 1 is always the one starting from the origin and ending to distal end. Okay? And the angle definition is, it is the angle of the inclination of the truss with respect to the horizon. Okay? If you want now to define 2 to 1, okay. But if you are going to use the same equation I derived before, the angle is going to be, how do you count this angle? Okay. We got to stick to our convention. Okay? So let me draw this out. This is my x-axis. This is my element. 1 to 2 has an inclination of theta. Okay, element 1, not 1 to not 2. But for the same element, not 2 to not 1, okay, how should I write it? If I take this as a not 2 as the origin, okay, there is only one way you can define the angle. This is your 180 degree plus pi. Plus theta. Okay? Please don't use theta anymore. Okay, in this case, because of the symmetry, so you cannot get true. But when you have more elements which might appear odd combination, the inconsistency in your angle convention will give you wrong answer. Okay? So get it? Define this way. Okay? Knot 1, and then knot 1 has the coordinate x1, y1, displacement v1, v1, force F1, F2. Knot 2 similarly can be expressed as coordinate, displacement, and the forces. Okay? And then how do you define the angle? Angle is obtained from the vector from knot 1 to knot 2. Okay? Your cosine angle is the ratio of the projected displacement in the horizontal axis divided by the total length, and then the sine, this is scalar, is the projection of into the vertical axis. Okay, we have designed all these. Okay, then you can finally obtain this stiffness matrix. Okay. It's the local stiffness, okay, times these whole bunch of matrices. Okay. Yeah, to help you understand better, we also have prepared the MATLAB code. So you just need to run these operations. Okay. So the reason we start teaching you MATLAB is so for trust element 1D, 2D you can all solve by hand. But at the end of this course, we're going to ask you to solve 2D triangle element. That is going to be 6 degrees of freedom. Okay? So then, yeah, by no means you have to handle matrix. So you better do it early. Okay, we start from this. Okay. So let's see. Okay, let me express this. So the first row is telling you okay, what's the coding here? The first row we define symbol K to be symbol in MATLAB, not a number, because MATLAB is a metric. They are good at matrix manipulation by number. Okay, but this one I have to define this as a symbol. You have K symbol, F1 symbol, U1, U2. Lowercase u1, u2 means the axial displacement. Capital U1, U2 means displacement in the global coordinate. Okay, so you can okay, we can rewrite this for clarity. So I can express this as V1, V2, V2. Okay. Okay, in matrix, we don't differentiate global displacement U1 and V1. To matrix, this is only vector component 1 and vector component 2. Okay? So here I have written you this K matrix, the stiffness matrix. Let's multiply them. You see, if I do define K as a symbol, there will be error. But now if I define the symbol, yeah, I can do symbolic operation. So you can see here, let me see how I enlarge my number. Okay, anyway, so yeah, you take your effort to see it, it's k minus k minus k k. Okay, this is a stiffness matrix. And then next, you define the force vector. You could possibly have the local force and local displacement. Okay? And then next, you want to express force vector as a multiplication of stiffness matrix with local displacement. Okay? This is just a normal operations. And then next, we try to define the rotational matrix. We define the symbol C for cosine, S for sine, and the rotational matrix is these expressions CS 0, 0. Okay, and then next, yeah, you can also express the, in this case, global displacement. Okay, this is the re-expression I have. Okay, so you can see the displacement vector. There are only two local nodes, but you can express in terms of the global displacement. And then next, you multiply the two. Okay, so you already have these expressions. Okay, and what they are just the force vector. If you have stiffness matrix and the local displacements, then you end up having the force vector. Okay, but these expressions, you can do simple simplification, and then the other way of doing that is you can do the expression here. Okay, this does not work because the multiplication we have to do it this way. Let's see. We have to multiply the dot. Okay. Then now you simplify. Divided by k, and then you simplify the final answer. Okay, eventually you have c squared minus cs plus cs minus cs. Okay, by these operations, okay, you have to do sorting. Then eventually you can get your stiffness matrix. Okay, if you are not sure what will it be, let me multiply this. So what do you have? And let me see. So you have the c squared, cs minus c squared minus cs. This being the matrix to be multiplied to the element stiffness. Okay. So with this, then we come back to the example of solution. Okay. How do you write these? How do you use this 2D element stiffness to write for a complicated equation? Okay, let's go one by one. Okay, for one horizontal element, because the angle is 0, cosine is going to be 1, sine is being 0. Then you have first row being non-zero and third row being non-zero. Okay? So don't be confused by these expressions, because the real meaning behind that is you need to know how does it tally with the displacement. Tally with what displacement is? It tally with this. if I'm not sure what this is, and I write this. We do multiply the impedance with the displacement, but just to let you know that horizontal element should have non-zero rho that match the displacement rho. This is non-zero matching with horizontal displacement. And then for the vertical one, you have the non-zero rho of the stiffness matrix matching with the non-zero displacement. Okay? Yeah. Even though we want you to master the matrix, but you should have the understanding of the reasoning behind. Okay, don't just treat yourself like a computer. Okay, because without your own proper judgment, then you're going to miss the calculation. The next thing you also need to know how to do is you must be able to do the calculation of the stress. Okay. So in finite analysis, this is what we call post-processing. So you have the two springs supporting the back. Then you can ask how much the displacement for the node 1, 2, U2, U2, this is 3, 4, this is your U4, V4. Okay? And just happen that 1 is 3. So how much the axial force acting on this piece of the spring, you make a cut of the spring, then you're going to have axial force. Remember, this is simply the Hooke's law. The calculation is just the stiffness times the local displacement, U1 minus U2. Okay? Yeah, if you need to do the expression there. Okay, but what is the local U1, U2? It's not that simple. You already remember U1 equal to U2, we express as the CS 0, CS, and then global displacement big U1, V1, U2, V2. Okay? So why I asked you to do the derivation? Because you see that this transformation of local displacement to global one, we have to use it so frequently. We should not have a second thought about how to re-express it. This is axial displacement. By rotation, we obtain displacement in the x and y direction in the global coordinate. And likewise, after simplifications, you finally obtain the stress is equal to E over L. Okay? So yeah, please go back and try it out. Then yeah. So okay, here how do we solve the questions? Okay. Sometimes to save you the trouble, people will say, I take the vertical axis to be the plane of symmetry. Okay, but that was done in the old day when computing power is limited. Okay, but today I think you better do the full model. Why is that the case? The symmetry of the geometry doesn't warrant a symmetry in solution. Because if the force is applied on the left hand side rather than the middle, there are no such thing as geometry symmetry. The force is not symmetry, we better do the full model. Okay? So, okay. Yeah. But by hand, yeah, you try to do symmetry. Okay, but by computer, no. Okay, so what you can see here is, for this question, so what is the solution there? The solution is, okay, if we have force symmetry, then we break this force into half the force, P over 2. We handle only one spring. But in this case, you are not using the theta as the inclination of the spring. You use 90 degree minus theta because your convention is angle above the x-axis. So, and then next, define how is the orientation. From knot 1 to knot 2, that's orientation. Okay? And the angle is 90 degree minus theta. It has a length of L, stiffness of K. Okay? And next, you apply the boundary condition. In this case, because of the symmetry, then this whole thing is restricted to move vertically. Okay? And then you can apply another boundary condition on the knot 2, which is fixed or anchor. Divided 2 is equal to 0. And then next. Okay? What else? By substituting the boundary condition, U1 is 0 for the anchor, U2 is 0 due to the symmetry. Sorry. I think knot 1 is at the bottom, so this is the free nodes. Okay? And knot 2 is an anchor, so they got 0 vertical and horizontal displacement. And then in the end, the force is acting on the vertical degree of freedom. This is minus P over 2 because it's pointed downward. So in the end, you only have one expression, K S squared times V1. So your answer of vertical displacement is force P divided by 2 times the stiffness S squared. And this is P over 2K sine this expression. This is becoming cosine. So this is exactly the same as we have derived. Okay? So by hand. So go back to our earlier exercise. Okay. Okay. How do we derive the vertical displacement? The vertical displacement, okay, can be obtained as the vertical force divided by vertical stiffness. This is 2K cosine theta. Okay. So that's the whole purpose. So everything starts from something simple. Okay. Why do we have to do this? Okay, another practice that you must master is before you do any modeling, if you can do by hand calculation, do it. Okay? And next, you can model it with simple. Something consists of a few elements. You validate them. Okay? Only when you have gained some confidence, then you start refining the mesh. The whole essence of finite element is not jumpstart a complicated thing without validation. So I know that this day, a lot of CAD software, computer-aided engineering software, has the computer-aided design software, has CAE as well, that's the analysis part. But without proper definition of boundary, that computation is just for fun, okay? Good for visualization. It's not more than any arbitrary cartoon. If you're going to use it for engineering purpose, please do your due diligence in checking, okay? Why even for the first element we did, we have to do this process, hand calculation first, and then do the final element analysis. Does it match with the time calculation. So this has been quality control for most of the finite element software. Okay. So why we need to do this quality control? You know, airplane can fall from the sky. If you don't do your due diligence, like what happened to Boeing 737 Max, you know, AI. How can you believe in AI? So there is one word that Elon Musk's friend tell the reporter: if you want to kill somebody, give him an autonomous car on the road. There will be high accident will happen. So you have to do your own due diligence to do the checking. Okay? No such thing as AI when you're on the road. Okay? You take your own responsibility. Okay? And then next we have validator. Next we come to the real problem. We have one of the simplest bracket to be solved. Okay? In this case, this bracket have one truss, two truss. Okay? Trusses. And now it's to be supporting a vertical force. Okay? What will be the deformation? Okay? To handle this, what we did is very simple. We do like British do, divide and conquer. Okay? Yeah. 2D truss already a challenge to me. Why not I break them up into two individual truss elements? The first one is knot 1 to knot 2. It has a property, okay, here. It is above horizon by 30 degrees. It has a length L, it has a stiffness of EA over 2L. Or what is the case is half length or something like that. Okay? Depending on how you define, I define this 2L. So this divided by 2L. Okay? And then next, what is the element 2? Element 2, I start from knot 2 pointed to knot 3. So in this case, the inclination is 180 degrees. Okay? And what's the length here? The length here is square root of 3 divided by 2 times L. And then what's the stiffness? Stiffness is EA over L. Okay? What NCs of finite element do is really step by step like this. They take your entry and then sort them in the proper table and then do the orientation. Okay? Yeah. Yeah. This is what is called the first database for your finite element. Okay? And then next, yeah, you do need a pointer for programming. If you do in MATLAB or in Fortran, okay, MATLAB is still okay, matrix form, but for Fortran or any programming, okay, they are just a series of data. You have to define them where to start the new row, where to end in the new column. Okay. So now you have two elements. First element, upon substitution of C being cosine and S being the sine, you finally obtain this stiffness matrix. Okay, this is simplified by factoring out quarter out of the matrix. Okay, so you have K1 over 4. On this side, okay, you go and check if it's, yeah, whichever you have, then you take this here. Okay, make a quick check. If it's right, okay, because this horizontal element, there should have non-zero row of stiffness in the horizontal collision. 3, 4. Okay. And eventually, you do the force sum. Okay? Well, we need to do the force sum because previously what we calculated is the element forces. But clearly you see that element 1 have a common knot, that is knot 2, sharing with the element 3. So if there is an element force on knot 2, it could happen to be contributed by On element 2, they could have force contribution for element 1 and also force contribution for element 2. So when you do the summing, okay, please do the right side. Okay? Force 1, force 2 on node 1 has no contribution other than element 1. Okay? Force 3 and force 4, which is the one on the node 2, okay, have contribution from both element 1 and element 2. And force 5 and force 6 acting on the node 3 have pure contribution from element 2. So by doing this force sum, then you'll be able to write Hooke's law, K times this complicated matrix, and then another contribution from the second element is all written here. So after this, then you do the sum bar. Okay, you really do one by one. But for the ease, we sometimes don't want to do it. We want to jump to the step. Okay, let's see what's the step we're going to do. Okay, I know this handling of the stiffness matrix is very, very troublesome. But let's apply the boundary condition first. Node 1 is anchor, no displacement, U1, U2, O, 0. Node 3 also anchor, U5, U6, O, 0. Only 3 nodes is 3, 4. So if I'm due in the examinations, what should you do? You should take up this, just copy down. Okay. Because I know I eventually need to handle this, I apply the boundary conditions. Okay, I won't take my effort to do the sum. Okay, on constraints node. I only try to handle 3 nodes. Okay. So what would I end up with? The 3 nodes happen to be in the this one. So if you are asked to handle, I only do the sum for these 3 nodes. Okay? Okay. And I could possibly go one step further. Rather than these complicated things, I just look at the one to do with the 3 nodes. Because I know the 3 nodes is going to be 3, 4. Then I'll just take the one to do with the 3, 4. Okay? So for real problem solving, you are not, you cannot handle so tedious thing. Sorry, this is not the 3, 4 that is constraint, this is the 1, 2. Yep. So you are handling the non-zero. Okay, eventually you come to take this out and solve for displacement answer. For last year. Yeah, I hope I don't need to repeat the midterm. Okay. So this sort of problem that we solve. I think later we will come back. How do you handle the class with distributed force? Because for our modeling so far, you handle spring. Spring can only handle longer force. Okay. A distributed force acting on the truss is equivalent to a pure truss with two normal force. Okay. And then since you're going to have two trusses, each of you can use the equations, but in the operations, you do the calculations, and then you do the constraint on the boundary. You only handle the non-zero displacement. You only handle the stiffness component that associated with the non-zero displacement. Okay, and then these two you do the sum. Okay, yeah. Please go back and try it out. You exercise with the right practice. Okay, I know that you could refer answer from your textbook, but your answer in the textbook doesn't help you because they are following the procedure which has no physical meaning. You better learn from your mechanics. Okay, Cook's law. Yeah. Then handle them properly. Then you get the right answer. Okay. So this sort of the. Okay, then we'll take a break of 15 minutes. We'll come back on the 3D truss.